Okay, there, AP scholars. Now we're getting to the meat and potatoes of the Unit 2 here. Okay, we get into the idea of Lewis structures. Hopefully you remember these and we're pretty good at them in the past. I'm going to be shifting views a bit here. I'll explain some stuff to you from the PowerPoint, but this is one of those things that you just got to get up and do. Alright, so with no further ado, let's jump into this. So you should know that a Lewis structure is like the dot structures we were talking about for elements, but now it is for molecules. Okay, so we're talking about covalent compounds. We're going to be representing valence electrons as dots. However, if the valence electrons are bonding, okay, a pair of dots would constitute a line, a bond. It is shared between two atoms. Okay, so that's the basic idea here. We're just going to be working on the idea of valence electrons and showing bonds, and eventually where that leads us, geometry, etc. So you should know there are two main schools of thought to this. Some people believe you should just follow the octet rule. Some people believe that you had to go by something called formal charge. We've talked about the octet rule already. The idea of the desire, if I may, of atoms to try and get to 8 valence electrons as it being the most important number there. So as we look at this diagram here, okay, again, remembering that a bond is a pair of electrons, we can see that we have 1, 2, 3, 4, 5, 6, 7, 8 electrons next to the oxygen. 1, 2, 3, 4, 5, 6, 7, 8 next to that oxygen. 1, 2, 3, 4, 5, 6, 7, 8 next to that oxygen. And if we look at the sulfur, we have 1, 2, 3, 4, 5, 6, 7, 8 next to sulfur. So everything is obeying the octet rule in this. So that model does seem to work. But when we talk about this idea of formal charge, which is really kind of the new trend, it's more the way that things seem to go, we're more worried about checking to make sure that everything is behaving the way that it quote-unquote wants to. Okay? Behaving in its more typical bonding fashions. Okay? So formal charge is a little calculation we do where we take the number of valence electrons on an atom, subtract the number of bonds, and then subtract the number of non-bonding electrons. When we do this, we get numbers, and hopefully we get more zeros than numbers. Well, than non-zero numbers. I guess 0 is a number. So when we can minimize formal charge, it's showing that the atoms are bonding more typically and equitably. I'm not sure if that's really what I want to say there. Let me explain it further. Let me go on. So if we go back to the first one and count out formal charges, looking at this oxygen here, we take its number of valence electrons, which oxygen has 6. We subtract the number of bonds, 1. We subtract the number of non-bonding electrons as 6 dots. So 6 minus 1 minus 6 means that this is -1. And this one would also be the same because it has the exact same setup. If we go to the other oxygen, it has 6 valence electrons, but now it has 2 bonds, and it has 4 dots. 6 minus 2 minus 4 is 0, so this has a 0 formal charge. Well, zeros are good, so that's all right. Then we go to sulfur. We see that sulfur has also has 6 valence electrons, and it's making 4 bonds, so 6 minus 4 minus 0, since there's no dots on it, is +2. Now, if we look at the whole thing, it does add up to be 0, so it does make sense as a compound that it would be 0, but the fact that sulfur is +2 and each of these oxygens are -1 implies that the oxygens were stealing electrons from the sulfur, and the oxygen, while very electronegative, isn't really strong enough to steal electrons, so there's some question about that. Now if we look at the other model, each of the oxygens is doing the exact same thing, so we have 6 valence electrons minus 2 bonds minus 4 dots, that's 0. So each of the oxygens are 0. And then for the sulfur, 6 valence electrons minus 6 bonds and no non-bonding electrons means that it's 0. Everything is 0. That's probably the way things want to behave. Okay? That's more of the ideal as is being defined nowadays. So let's talk about how you get to those pictures and the steps for drawing Lewis structures. Maybe you remember it, maybe you were told a different way. This is the way I'm going to explain it right now, for the video purposes at least. So the first step is going to be to calculate the total number of valence electrons. So for example, if we're talking about that SO3 model, SO3, I know that sulfur has 6 valence electrons, each of the oxygens has 6, so that means there are 24 valence electrons on this. So my first step would be to calculate the 24 electrons. Identify the central atom. Okay, it's one with the lower or lowest electronegativity. There's multiple ways of looking at this. Okay, sometimes I tell you to think about the elements that want the most bonds. That wouldn't really apply here. It does come down to electronegativity. I make a point of saying hydrogen and fluorine cannot be the central atom. Why? Well, to be central implies that you're making more than one bond, and hydrogen and fluorine only will ever make one bond. Hydrogen, because it only has one electron, so it can only make one bond, and fluorine, because it is the strongest element and it has 7, it's never going to give up another electron, so it's only ever going to make one bond. So keep those two in mind. All right, so we know sulfur is a central element. We're going to put oxygens around it. I'm just going to go here, here, and here. Now we want to identify the number of bonds the outer elements want. So if my outer ones are oxygen, which has 6 valence electrons. So we're going to take 8 minus 6 and say that each of the oxygens wants 2. So I'm just going to go right in and give each of the oxygens 2 bonds. Now we're going to calculate the number of electrons remaining. So each bond is 2, so 2, 4, 6, 8, 10, 12. I've used 12 electrons. That leaves me with 12 more. So now what we want to do is complete the octets of the outer atoms. So I'm going to go to these oxygens and I'm going to say, all right, right now next to this oxygen is 4 electrons, 2, 4. So I'm going to give it 4 more. And do the same for this one, and do the same for this one. And 4 plus 4 plus 4 is 12. That leaves me with nothing. And if I've done this right and I have nothing left, I should be done. Okay, that's all there is to it. You'll see that there are a couple other steps, because if we do have extra dots at this point, they would have gone on to the central atom. And if it was an ion, we'd have to take that into account and also draw brackets around it just to show that there is a charge on it. So let's go through that a little bit more. Okay, a couple of things you want to keep in mind. It is possible to have single bonds, double bonds, and triple bonds between any two elements in the structure. Again, hydrogen and fluorine, never going to do that. Okay, because they only make one bond. Done. The outer elements always obey the octet rule, although for hydrogen we call it a duet, because hydrogen can't do more than a bond. And that's it. If there is a negative charge, so if we're talking about a polyatomic ion with a negative charge, the negative charge must be on one or more of the outer atoms. But if there's a positive charge, that must be on the central atom. Some elements cannot obey the octet rule simply because they don't have enough electrons, boron being the most common. It has 3 valence electrons. And so how do you get to 8? It can only, if it has 3, it could share 1 here, it could share 1 here, it could share 1 here, and that's it. It's going to make 3 bonds. That's going to get it to 6. We're also going to see that elements after silicon can exceed an octet. What do you know? We already saw that right here. This sulfur has 2, 4, 6, 8, 10, 12 electrons around it. That's okay because sulfur is after silicon. And that has to do with something called hybridization, which comes up later in the unit. So for now, just understand that it's any element after, not including silicon, any nonmetal after silicon can exceed an octet. And yes, it is possible once in a while that you're going to end up with an odd number of electrons, and so you can't pair everything up. But it's very rare, and it's that's not really going to come up all that much for us. All right, so here is me going through that same example that I just did on the board. But let's talk about a chlorate. So let me, actually strip views here and do it for you the old-fashioned way. Let's go OG. All right. So let's talk about a chlorate ion. All right, so first thing is to figure out the total number of valence electrons. So chlorine has 7. Each of the oxygens has 6, but it's an anion. That means I have one extra one. So 8 and 18 means that I now have 26 electrons to take care of. I don't really have to question that chlorine is in the middle of this. I know it's lower in electronegativity. And the fact that there's 1 chlorine and 3 oxygens kind of helps spell that out too. Now, we talked about the idea that we got to give the elements what they want. But this is a -1 ion, and we said that that means that one of these has to be have a negative charge on it. So one of them doesn't have 6 valence electrons. One of them has 7 valence electrons. So we arbitrarily pick. I'm just going to say this is my guy that's going to have 7. So because it has 7, this guy only wants 1 bond. However, these two have the 6, and so they want 2 bonds. So we're going to stick to it like that. So 2, 4, 6, 8, 10. I'm going to take away 10. That means I have 16 electrons to go. So now I start filling up octets. So this oxygen has 2, 4 next to it, so I give it 4 more. This oxygen has the same, I give it 4 more. But this one only had 2 next to it, so I have to give it 6. So 6 and 4, 4 is 14. And that's going to leave me with 2. Those 2 have to go on to the chlorine. Now, this is a polyatomic ion, so now I have to do this, and that's it. Now it is a complete Lewis structure. All right, let me throw out one other one. Let's do HCN, hydrocyanic acid. Hydrogen has 1 valence electron. Carbon has 4, nitrogen has 5, so that's a total of 10 valence electrons. Looking at the periodic table, I know that carbon has the lowest electronegativity of these. Again, hydrogen can't be in the middle, so just don't even consider that. So it's got to be carbon. So we're going to put hydrogen and nitrogen just like the formula kind of shows. The outer elements get what they want. Hydrogen only ever wants 1 bond. Nitrogen wants 3. So we're going to give it 3. That's it. So that means 2, 4, 6, 8. We've taken away 8 electrons. That leaves us with 2 more. Okay, we make sure the outer elements are happy. Well, hydrogen only ever wants a duet. So I come over to nitrogen. I give it 2 more to give it its octet, 2, 4, 6, 8. That uses up to 2. We should be done. Now, it wouldn't hurt to check the carbon, because carbon is one of those elements that always obeys the octet rule. And sure enough, it does have its 8. All right, so this is where you pretty much just need to practice. Try some of the ones that I put linked in for you before you do the AP practice in the classroom. All right. And by all means, let me know if you have any questions. Ciao for now.